And you'll notice that I've integrated that into here. The learning objectives are actually really short. We're just wrapping up a little bit on what we had learned last class. We did all of Redox pretty much last class period. So today all we're going to do is use changes in oxidation numbers to balance chemical equations by looking at the amount of electrons transferred. So that is the only objective for today's lesson. But before we go over that, I wanted to give you the revised schedule on what's going down as we wrap up on Unit 3. We're actually, after today, we're almost done with content. There's only one more lesson I'm going to do with content next Monday, and that's going to be about group 17 halogens and redox with group 17 halogens. That's usually a topic I do at the end of the year, but I told you I was trying to integrate that last unit into earlier parts of the year so you wouldn't have this weird 3 or 4 lesson unit at the end of the year. So one of those lessons that I usually teach at the end of the year, I'm actually teaching next week on Monday because it actually is the redox reactions of group 17 elements. And so we'll be doing that next week. That's going to be the final lesson of the unit. So what are you going to be doing the rest of the time? Well, today we are finishing redox and going over the lab math that you need to know to be successful as we start practicing for paper 3 more. Then you're getting the written homework for redox today. It'll be due on the 8th, which I believe is Wednesday. I'm giving you time if you messed up on the last homework or you're very confused on the other math homework. Come to tutoring tomorrow. You can work on that homework and still turn it in for full credit because I wasn't here last week. Or the one that I'm passing out today. You can work on that and turn it in for full credit. So just be aware. I want to repeat that again. If you got really confused on the last homework that was due on quantitative analysis and concentration and gas law, I'm still accepting that for full credit if you come to tutoring tomorrow and you turn it in afterwards. I understand I wasn't here last week, and so if you do need assistance on those topics, make sure you're coming to tutoring. After tutoring tomorrow, during lunch, I'll be setting up for your lab, which will be on Wednesday. And it will be almost a full class lab after bell work. We're just going to go over a few things you have to know to be successful in that specific lab, and then you'll have about an hour, at least an hour and 15 minutes to maybe an hour and 30 minutes to do the lab. It'll be a long lab session. But it'll be a full titration, and you need to do everything correctly. We're going to go over what that means today. So that titration next class is a graded lab. It will be graded on a Cambridge curve, but it will be graded using Cambridge marking system. And then on Monday next week, because remember there's no school on Friday. So Monday next week, we are going to wrap up on redox of group 17 elements. And so that will be, the redox of group 17 elements. That's what I said. It's usually a topic that I cover later in the year, but I'm trying to bring some things to the earlier part of the year and not have to do a weird half unit at the end of the year. So I added that lesson in, which extends our time just a little bit longer. You'll get the last written homework next week. That'll be due next week on Thursday. And there will be tutoring next week as well on Tuesday. This and next week are going to look very similar to each other because today on Monday, lesson, Wednesday, lab. Next week, Monday, lesson, Wednesday, lab. Actually, so we're going to do titration number 3 next Wednesday. Also a graded lab, and that'll be specifically a redox titration. So we'll be looking at the key differences of what is a redox titration versus a regular acid-base titration. On Friday, November 17th, we're just going to do some practice, probably Kahoot or quizzes, something fun, because we are the very last class before Turkey Bowl. So just so you're aware, November 17th, that's going to be just a practice question day. When we come back from Thanksgiving break, we'll have a full review day, the Tuesday, November 28th when we come back. And you'll have your quizzes due the Tuesday, November 28th. So you have all of Thanksgiving break to work on it, or if you choose not to work on it during Thanksgiving break, you can work on it the Monday and Tuesday you come back from Thanksgiving break for the paper 1 quizzes, which will be hefty. As you can see from the questions you've seen with the math questions, they can take a little while to solve. And so you may want to get started on it early. I'll be posting it next week. Or you can wait and procrastinate. It's up to you which way you want to go with it, but it is a hard deadline of November 28th. And then Thursday, November 30th is our Unit 3 exam. We'll end the month with this unit being done on quantitative analysis and redox. And then starting beginning of December, we're starting organic. We're going to start organic in the first week of December. So that's where we'll be going next. All right. So just a couple lessons left in this month, today and next week, and then labs, review, test at the end of the month. That's what it looks like. No more Redox? Redox. So for those of you who were missing last class, you missed a hefty lesson because we did pretty much all of Redox. Redox is the transfer of electrons between elements in a chemical reaction. That's what it is. So redox is transfer of electrons between elements in a chemical reaction. Not all reactions are redox, but anytime your charge changes, your oxidation number changes, from reactants to products, you have redox. And so there are specific types of reactions that are always redox and specific types of reactions that are never redox. But in redox, there is always a transfer of electrons. So you see here in this formation of sodium chloride, where sodium gives away its valence electron and chlorine receives that valence electron, that's an example of redox, because sodium is giving away its electron and chlorine is receiving. In this diagram, what's being oxidized, sodium or chlorine? Sodium. Because it's losing its electron, Leo. And then what is then being reduced? So this is oxidized, and chlorine is reduced. Yeah. And so that's just, a quick what we did last class, a very, very simple version of what we did last class. We went over how to solve for oxidation numbers of all various types, and then we learned how to recognize what's being oxidized, what's being reduced, and then knowing whenever you're looking for agent, you're looking for the opposite of what's being oxidized or what's being reduced. So all we had left to do in redox really was balancing redox reactions using electrons. So I wanted to show this to you, and this is actually one of the types of labs that I'm going to give you next week on a titration. Is actually, instead of an acid-base titration, there's something called a redox titration. In an acid-base titration, we talk about transferring H+ from acid to base in an acid-base reaction. But in a redox reaction, we're actually transferring electrons in a redox titration. So let's take a look at this checkup. It's using half reactions to balance chemical equations. What would you do? You want to balance this equation. Construct a balanced ionic equation for this reaction using two half equations below. By looking at these two half equations, can you tell which one is the reduction half equation and which one's the oxidation? Is this top one a reduction or an oxidation? How do we know? The top one is a reduction. Because electrons are going in. If electrons are on the left-hand side, it means electrons are going in. And if you were just to trace with their numbers, the oxidation number of iodine here is +5, and here is 0. Its oxidation number goes down. It's reduction. What about zinc? And there's a plus missing here, but it should be Zn2 + 2e-. Is that reduction or is that oxidation? Oxidation. Can you ever have two reductions without any oxidation? No. If you have red, you must have ox. If one element is gaining electrons, it must be gaining them from somewhere. It is a balanced transfer of electrons, meaning one is giving away and the other one is receiving. And so now that I've diagrammed which one's reduction, which one's oxidation, how do we balance this equation? What's not balanced here that you think should be balanced for redox? Well, what is redox again? What did I just say it was? Transfer of electrons. So in your reduction, you're saying that this iodine technically gains how many electrons? 10. Do you agree? And in the second reaction, we're saying, well, hey, zinc gives away how many electrons? 2. So if one needs to gain 10 and the other one loses 2, is that an equal transfer right now? No. So what you have to do is you have to balance the electrons. So step 1, balance electrons. How do we do that? You have to make the amount of electrons transferred be same. So make the amount transferred the same. Do you think it would make more sense to take 10 and divide by 5 or take 2 and multiply by 5? Which one sounds better? Multiply by 5. Because if you take 10 and divide by 5, you're going to have 1/5 of an iodine, and that doesn't make any sense. Like if you do that across the board. So make the amount transferred the same, which means find, what is it called? The first number they go into, is that called the lowest common denominator, we would call that in math? Lowest common multiple? Find the lowest common multiple, which means just find the first number that 2 and 10 go into, which is the first number that both 2 and 10 go into is 10. So we would need to multiply the bottom equation by 5 to match the amount of electrons. So that's what we do. Step 1, balance the electrons. Once we have balanced the electrons, we rewrite the equation. So when I rewrite it, I'm going to have now 2iO3 minus plus 12H plus 10E minus goes to I2 plus 6H2O is the first one. I didn't change anything about that. And what would the bottom one look like? The bottom reaction, the oxidation.
5ZN.
5ZN goes to 5ZN, 2 plus 10E minus. So then once you have the same amount of electrons going in as you have coming out, you, like you would in math. And then you bring everything else together. You rewrite all your reactants together, and you rewrite all of your products together. So it's rewrite equations and then combine together. So what does that look like? For all of my reactants, I would want to write everything that's on the left-hand arrow as one line. So it would be 2iO3 minus plus 12H plus 5ZN. And then on the other side, we would write I2. So it's just all of this stuff. And then you don't write the electrons because they're right, just as you see it. 5CN2 plus, and that's it. And that would be the full redox. So when you see the full redox equation, oftentimes you're going to see that the spectator ions are not shown. And you're only seeing what's happening in terms of the electrons that are being transferred. This is actually very similar to the type of reaction I'm going to give you next week when I give you your third titration lab. I've been looking into giving you a starch and iodine titration, and that's what this is going to be, which is an interesting one. It's an interesting titration. And so the difference between an acid-base titration and a redox titration is in an acid-base titration, we're talking about an acid neutralizing a base, whereas in a redox titration, we're talking about a transfer of electrons. All right, I have just a couple more questions here. See if you can combine these two half equations to make a full reaction. See if you can follow what I did. This looks a lot simpler than the one I just showed you. But see if you can follow the same strategy, the step 1 and the step 2. a minute or two to work on this, and then we're going to continue. Check to see if you've got the idea. Yes, very good. Looking at your date. It's remember I posted on the schedule. It's actually but
You get Sorry, thank you, buddy.
all right. Ready? See? Bueno. Yes, you may.
Simple stuff. Not that much.
You know? All right, so I'm going to go ahead and show it. First of all, let's just practice with this because I know we only did one lesson on redox so far. The left equation, is that reduction or oxidation?
So it's reduction.
Reduction. And this is the
Oxidation.
oxidation. But from the half equation to put together the full equation, the amount of electrons that's gained by one has to be the same amount that's lost by the other. And you should always increase the amount. So don't divide both sides by 2. Multiply the one with only one electron by 2. And so we multiply this equation by 2. We get 2Fe2 plus, and then 2Fe3 plus E minus, or 2E minus. You distribute the 2 just like that to every term where you have the plus sign in between. Yes? Because then, well, here you technically could. For this example, you could, but in the last one, you couldn't because you would have like 1/5 of an iodine or 2/5 of an iodine. So as long as you end up with a full amount of all the atoms, it's okay, technically. So you could in this one, but you shouldn't. Just be careful. So then here, I write all of what's on my reactant side and all of what's on my product side except I cancel the electrons. You should show that you cancel the electrons because only once the electrons cancel should you be able to combine your half equations together. And so you get Cl2 plus 2Fe2 plus for the reactant side. And for the product side, you get 2Cl minus plus 2Fe3 plus. And that is the product side. And so that's what we do when we need to combine half redox reactions together. Balance the electrons, then bring everything else together. So the next thing I wanted to show you is a quick aside into naming. In pre-ACE chemistry, which I'm actually teaching this topic right now in pre-ACE chemistry, in the naming of polyatomic ions, Cambridge actually asks you to memorize a lot less than an American curriculum would ask you to memorize. So I'm just gonna throw this out there. You have to know that SO4 2 minus is what? Sulfate. In an American curriculum, you would also need to know what SO3 2 minus is,
Sulfite.
which is sulfite. And you would need to know what SO2 2 minus is, which is hyposulfite. And there's this whole thing where if you take away one oxygen, it changes to ice. If you take away two oxygens, it changes to hypoice. And if you add an additional oxygen, it changes to per. And that's the American naming. If you recall, Cambridge only asked us to memorize this. They don't ask us to memorize the difference between sulfate, sulfite, hyposulfite. They don't do that. Like, that's not a thing you're ever going to see on a Cambridge question. So why not? Why do they do something a different way? So here's how they do this instead. SO3 2 minus, if they presented it to you, they would actually call SO4 2 minus sulfate 6. SO3 2 minus, they would call sulfate 4. And SO2 2 minus, they would call sulfate 2. That is the Cambridge method. So what is being told to you here? Go ahead. A Roman numeral. And what do you think that Roman numeral? Represents when Diane gets back? Oxidation number of sulfur and all the different variants. So the way that Cambridge teaches systematic naming, I just wanted to go over because this is the way it's going to be presented to you when you're looking at questions, especially on paper 1, but also on paper 2. If they were to give you ClO3 minus, the way you do it is you just say Cl is chlor, and the ending's always going to be 8 for Cambridge. So it's chlor 8. But then what they do is they write a Roman numeral to say what is the oxidation state of chlorine. So what is the oxidation state of chlorine here? It's ClO3 minus 1, right? What's the oxidation state of 5? How do we get 5? We know that oxygen is -2. The whole thing is equal to -1. So I'm just re-showing how to do it. Cl minus 6 equals -1. Add 6 to each side. +5. You could also get it a quicker way by looking at the formula. But it's chlorate 5. That is how polyatomic ions will be referenced furthermore in this class. You're going to see a Roman numeral, and you have to understand that the Roman numeral means the oxidation state. So they're telling you the element besides oxygen, what is its oxidation state? That's what that is meant to communicate to you. So then, really quickly then, what would ClO minus 1 be? Because this is a thing that exists. And you're going to see it next Monday in next Monday's lesson.
Chlorate 1.
Chlorate 1. That's right. Chlorate 1. Because chlorine here has a +1 oxidation number. When oxygen has a -2, chlorine has to be +1 for that to balance out to be -1. So you would see that as chlorate 1. I'm teaching you this to tell you, well, first of all, this is how Cambridge is going to do things from now on, so we need to be familiar with it. But also, if you ever see a question, you're just looking up chemistry stuff, and you see sulfite or hyposulfite or all that weird stuff, it basically does not apply for what we are doing for international chemistry Cambridge, okay? We use this method, the systematic, it's called the systematic name. Which, be grateful you use this strategy because the other strategy is a pain. to memorize. Alex? All right. So then what is the systematic name for KMNO4? K is just potassium. MnO4 is one of those polyatomic ions you've been asked to memorize. What's it called?
Manganate.
So it's actually manganate or permanganate. You can use either. Cambridge is actually going to call it manganate and not use the per because they actually just do manganate and then what is the charge of manganese here? The oxidation number. What do you think the oxidation number of manganese is here?
Four.
No. Maybe work it out. I don't know. Potassium is +1.
Oh, so 7.
Oxygen is -2 times 4. So -8, +1. Whole thing has to equal to 0. What does that got to be?
7.
+7. So it actually called by Cambridge on a paper 1 question, they would call it potassium manganate. 7. Potassium manganate 7. And so the whole per, the it, all that is not really used by Cambridge. Instead, they use something called the systematic name. And so what I need you to be able to recognize, and whenever you see a Roman numeral, that is being intentionally communicated to you to tell you the oxidation number, which is kind of nice because if you're looking to do redox with that, they've already given you what the oxidation number is. So just FYI, know this, be aware of it. It's going to show up in questions. It'll probably show up in your lab next week.
Wait,
All right.
which one's being constant?
What? The constant is always the first element, and the last element listed, you're always solving for the one in the middle.
Oh.
If you have an ionic
So the charge
compound,
of manganese is the one.
yeah, that's the one you'd be solving for. The charge of manganese is the one, just like, and then for ClO3 minus, it's a polyatomic ion, you always know oxygen you'd have to be solving for chlorine, because that's the only one that can change. So then, this is a practice question. This is from the 2020 exam series. And I made sure to give you a different one in your homework. I looked and this was originally the one I had in the homework last year. But I like to change things up every year. So I'm doing this one in class this year and give you a different one that's similar in the homework. And so let's take a look at what type of question you'd be given. It says, the equation shown in A1 describes the reaction which occurs when aqueous potassium iodide is added to aqueous copper 2 sulfate. And so now we know, oh, Roman numerals always used to tell oxidation state. So that means that copper has to have +2 charge. A white precipitate of copper 1 iodide forms in a brown solution of iodine and potassium sulfate. They ask you to balance the equation and include state symbols. One of these things I haven't explicitly taught yet, and technically you have to get it just from reading it here. And so CuSO4, can we figure out the state of matter for that? Do they tell you in the question? So you should write in AQ. Do they tell you the state of matter for Ki?
Precipitate to solid.
Ki.
Oh.
It's in the first sentence, right? Ki, aqueous. But they do say, and I think this is what you were reading, a white precipitate of copper 1 iodide. So what does that mean, copper 1 iodide is?
Solid.
If it says precipitate, that means solid. Now the next one, and I've read this mark scheme, because you wouldn't necessarily know, so they give you a couple of different ways to understand it. They say solution. What is the state of matter for solution should be? But solution is a combination of more than one thing. So aqueous. But they accept, and because there is confusion there, on this specific mark scheme, they actually accepted aqueous or liquid, actually. But aqueous is technically solution because you have to have solute and solvent. And then K2SO4, What's the state? Did they tell you? A brown solution of iodine and potassium sulfate. Solution of potassium sulfate is also AQ. How many points have I earned so far?
One.
One for the states. So where's the other mark?
Balance in the equation.
Balance. Is this easy or hard to balance? What do you think? It is easy. You've got two iodines on the product side. So what do you need to put in front of Ki?
Two.
You've now got 2K, 2K, 2. Actually, it's a little bit more difficult. You've got two iodines plus 1. You've actually got 3. Can you see that? That's a slight issue. So now what?
Now they have K2 as a 4. Oh, 2.
There you go. 12.
How'd you do it? What? I would say if this has got to be a 3, then this has got to be a 6. So I would put a 3 here. And I would make this a 6 instead. That's what I would do. Then I would do 3. 3. What else are we missing? We need one more iodine. So what will we do for that? Because right now there's 5, right?
Yeah.
We need how many? 6. So I would do 1.5. Does that make sense? Check it out. 3 coppers, 3 coppers, 3 sulfates, 3 sulfates, 6 potassium, 6 potassium, 6 iodine, 3 plus 3 is 6 iodine. That's it. Is this okay to have decimal? Yes. Could you have also doubled everything?
Yes.
Sure. So you could have done this as 6, 12, 6, 3, and 6, which could then be simplified by 3.
Yes.
If you did that, you would get. Do you have to simplify? If you have something you can simplify, then you must. So 2, 4, 2, 1, and 2. 2, 4, 2, 1, 2 would be also the correct ratio.
Okay.
2, 4, 2, 1, 2. So if you did 3, 6, 3, 1.53, or you did 2, 4, 2, 1, 2, those are both correct as ratios. So kind of level maybe 2-ish balancing, right? Because you had to go back and forth a bit. I would call that a level 2 on the balancing. Level 2. Definitely not the easiest it could be. What about the next point? Deduce the oxidation number of copper. Is this something that you could get pretty easily? Don't they say in here is copper 2 sulfate? What's the oxidation number of copper?
2.
Right?
Copper 1.
And don't they say copper 1 iodide in the sentence at the top? So what is the charge of copper?
1.
Plus 1. What level you want to call this?
1.
This is about as simple as they could give you a question yes. Because it said precipitate. Precipitate means solid forms of that specific thing. That's what PPT means. Yes. Yeah. All right. So that was some redox questions, just so you're aware of what type of questions you could get. This was paper 2, and you will get a variety of more paper 1 and paper 2 questions in the homework today that I'm giving, the classwork. But before that, I think it's really important that I go over the math with you for the lab. You know that there's a chance you get a few math points on paper 2. You know there's a good chance you get a few math points on paper 1. Paper 1 being multiple choice, paper 2 being the written exam. you can 100% guarantee you've got math on paper 3. And it's very predictable math. So what we're going to do now is we are pulling out your labs. So I gave you your lab papers back last class, or last few minutes. Pull those out. Get a ruler. I'll give you one. And we're going to go over how to get the marks correctly. So next time when you have a lab, you can have a graded lab. I don't feel comfortable grading something without having pre-taught you how to do it. So.
Amen. We're doing it.
We're going to go over your lab so that when you have a real titration next class, you are more prepared for it. I'm passing out more rulers. If you have your own ruler, feel free to get your own ruler. Welcome back. All right, we're going to start to go over the labs now. All right, so let me get your full attention for this because this is something you need to be well aware of. Yes. Go ahead. This is something you need to be well aware of on how to answer. And so what I have printed out here and what I gave you back was your labs. I'm going to go through and give you some sample data on how to answer the questions correctly. This is not to say that your work was right or it was wrong, because you all had different masses to measure, which would affect your final answer. I'm just going to give you some sample data to work off of so that you know what to do when you have a lab next time. So you get a lab. Paper 3. You have instructions in front of you. What's the first thing you should do? Read the instructions and follow them thoroughly, right? So we're going to go back over this just so we remember what we did. It's been a couple weeks, so just so we remember what we did. What they're asking you to do here is calculate the relative atomic mass of some kind of metal by titration. And they tell you that you've got Fe2. You should point this out for yourself. You've got that number. What is that number? That's concentration of acid. You've got concentration of acid given to you. We're going to need that when we get to the math later on. So it's important that you read and you identify what's being given to you so that you know what pieces of information you have to help you solve later on. You've got Fe3. This was some kind of solid. You may have forgotten, but the first thing you did was you measured the mass of some solid and you put that into the solution you were making. And then Fe4 was your methyl orange indicator, and the color you were looking for methyl orange is orange. You're going to have, I'm going to go over what color you're looking for next class, but the indicator you're going to work with next class is bromophenyl blue. That's the one that I'm working on for you to work with next class. I want you to get to work with a full variety of indicators as we go through the year. So the next one we're working with is bromophenyl blue. So first thing you did, you weighed the stopper container. It says record the mass in the space below. How do we record masses properly? And so mark 1 out of, there were 16 marks in this lab, is recording the data from the weighings. The best way to go about this is to use the information they give you. It says weigh the stoppered container. So we would put mass, stoppered container. But what else is in that stoppered container? What is in there? So then I would put plus Fe3, because Fe3 is in that stoppered container. Because remember, we poured it out. And so massive stopper container plus Fe3. And then you have some amount of grams. You must include the unit of mass when you are measuring the mass. Like, you have to write it down. If you don't write the unit, you're going to lose out on that first mark. So I'm going to give sample data. I had 25.70. You're gonna wanna write down the sample data. You can write it in the lab because I have everything printed out for you for the whole thing, or you could write it on your own lab paper. It's up to you. Whichever one you want to, you have both of them to look at. And then it says tip all of the FB3 into the 250 centimeter cube beaker and reweigh it. Record the mass. So how would we write that properly? Mass of the stoppered container. But this time there is no FB3. So what do you expect? The mass goes up or it goes down? It definitely goes down. And so I have for my sample data 24.40 grams. So then it tells you, so I've done this, I've done this, I've done this. Are you allowed to check mark as you go along and you're doing the lab? On your own lab paper? Sure. You should keep track of where you're at. And then it says calculate and record. So you see that word record means you need to write it down. That means there's a mark associated with this data gathering. Calculate and record the mass of FB3. How do you get that? Right. Which you can do in your calculator. You do not have to show I subtracted these two numbers. But you should understand the answer here is 1.30 grams. Does that make sense? Because in order to get the mass of FB3, you would subtract the two masses you got. And so this is your mass of FB3, which is your metal carbonate. That's where we're at so far. We know that we have 1.30 grams of that metal carbonate. Then we took it, we made the solution, we stirred the solution, we put that into a 250 centimeter cube flask, and we label it FB5. What does a volumetric flask look like? You remember? It's the skinny one that looks like this. So if you need to label a solution, it's gonna be the volumetric flask, FB5. So you should write that because you are gonna go back and you're gonna have to answer math about this stuff. So you need to know what is your different things that are labeled, right? So FB5 is this 1.3 grams that was dissolved in 250 centimeter cubes of there's only a couple extra copies of the lab paper. You have to be very careful with the lab paper.
No, I mean the actual class.
Oh, that's a great question. So if you went over and you have to redo everything, you have to make your solution again from scratch. We are instructed to make 25% extra. So that means for 18 students, there would be about 5 extra setups. That is a just in case. And I usually am overbearing, meaning I do more than that. I usually do like 50% extra just as a just in case. So if you're allowed to raise your hand on a Cambridge exam and ask, Miss, I ran out of FB2, can I have more? Or Miss, I need more FB3. And then we would get you what you need. We're not allowed to answer just like any other Cambridge exam question about the content of the paper, but we are allowed to give you more materials if you need more. We get all the questions asked and answered here about how to help out with how to answer the lab. All right, so are we good so far with this first page, what I went over? Out of the 16 marks of this lab, we've earned 1. We've earned 1 mark for recording this data correctly. So make sure that you're writing down what you need to do as you go along. I'm going to leave this up here for just a little bit longer, and then we're moving forward. Yes?
This part, we don't have like something.
No. This is just for understanding because we're going to go over the math later, and you need to know where everything's coming from. So all the math in the lab comes from the actual work to do.
How much time do you give it for?
You get 2 hours for 3 labs typically.
You have to do 3 labs?
Yeah, but you'll reverse them several times. So by the time you get to that day, your students generally finish on time. At first it sounds overwhelming, but don't stress it.
I'm slightly concerned.
I said on time. I didn't say early.
No, I was.
Oh, for that one? That one?
I would say on time is fine.
24.4.
I have stories,
No, she said
but
that was just nice.
not at this moment. All right, so let's continue. You'll see as you move forward, we're going to move to the next page. It says, fill the burette with Fe2. Pipette 25 centimeter cubes of Fe5 into a conical flask. You have to memorize what is a conical flask versus what is a burette. So, what is the burette?
Like a long.
Right? This has FB2. And then what's down here? What is this thing called?
Oh, the conical flask.
That's the conical flask. So you're going to want to write that down because although you don't have to memorize a ton of different equipment names, this is definitely equipment names you're going to see a lot. Conical flask. In the conical flask is what? What do they say?
FP5.
FB5.
25 centimeters cubed.
25 centimeters cubed. There's also something else in there, hopefully. FP4. What's FP4?
That will,
That's your indicator.
oh yeah.
So, indicator. And what happens if you forget indicator?
Doesn't change color.
Color will never change. You start with a colorless solution. You end with a colorless solution. You use all 50 milliliters. You cry. So don't forget to add the indicator on Wednesday. Is all I'm gonna say. I'm giving you the heads up now. So we've got FB2 titrating with FB5. FB2 being what? HCl. And FB5 being some kind of X2 CO3. Just so you know, that's the actual chemical reaction that you're doing. You're mixing hydrochloric acid with X2CO3. And so your next mark, your second mark, yes.
If what you do is taking that diagram, the actual temperature thing. If they don't say how much you should use, how much do you?
I recommend 10 drops if not cold. I recommend 10 drops, which is equivalent to about a milliliter per centimeter cube. It's better to go heavy-handed than too light because you can see the color better if you add more. What I will suggest though, Rosalind and everybody else, is that you add the same drops to each trial. Because if you add different drops, your colors will end up looking different and it'll be harder to tell where the end point is. So initial volume should be always what in your burette? Where's the top here actually? Actually, 0, 0 at the top and it's 50 at the bottom. And you're measuring the difference as you add down. So your initial volume should be either 0.00 or very close to that. Depending on if you get it exactly to 0 or not, it's up to you. You can rush, but then write down your data correctly if you don't exactly get it to 0. So then 0.00 is your initial. I'm going to give you sample data again. Final volume, this is close to what my lab aids got, 24.75 centimeters cubed. And then you've got to know to subtract those two numbers to get. It's going to be your final minus your initial is the amount added. Which is 24.75 because 24.75 minus 0 is 24.75. So the second mark is to write the initial and final for the rough titration. Meaning if you just wrote 24.75 and you didn't write what your initial volume was and what your final volume was that led to that, you don't get the second mark. that's why I'm slowly going over with you. This is how you earn the marks. They're actually very easy to earn because they're the same every time. The first one was, in this case, recording the mass. The second is recording your initial and final volume for your rough titration. What was a rough titration again? What's another way of saying rough titration? Fast or test titration. We just want to know the area where the color changes. Once we find the area where the color changes, we start working out the accurate titrations from there. All right, I'm giving you some time. And then we're going to continue. So this is Mark 2. And so next class's lab, I expect you to have all of this information done correctly. On the next slide, what you're going to see, and in your lab paper, you're going to see a 1 through 8 here. Do not write here. Do not. This is where the Cambridge examiners mark whether you got it or you didn't get the mark. So they either put like a 1 or a 0 there. A 1 if you got it, a 0 if you didn't get it. And so do not write in this little area right here. You leave that blank. But I am going to describe. We actually already saw Mark 1, the mass weighings, and Mark 2. We saw the recordings for the rough titration. So rough titration. I'm now gonna tell you what the other marks are. The easiest marks, or the hardest marks, depending on how you look at it, are marks 6 through 8. These are your accuracy marks. Marks 6 through 8 here are for accuracy. Meaning, how can you control accuracy? Clean equipment, follow instructions properly, make sure when you're making your solution everything is dissolved very thoroughly. Don't go over the line, don't go over the mark. So that's how you control accuracy. Have clean equipment. So making sure that before you begin that all your equipment is clean. Other than that, you can't control accuracy, can you? And you'll have no idea on the Cambridge exam whether or not you were accurate. You try for your accuracy marks, but they don't make or break your exam actually. It's only 3. And there's 16 marks in this specific lab. So that means there's 13 other marks that are not the accuracy marks. So then let's take a look at what is Mark 3. Mark 3 is the headings of your accurate titration table. And so this is where you may want to have a ruler. I won't be working with a ruler, unfortunately, on the screen here, but you may want a ruler. You're allowed to have a ruler. Are you allowed to write in pencil for the table?
Yes.
So you're going to write initial volume, and you should write /centimeter cubed as your first heading. Initial volume /centimeter cubed. The second column is final volume /centimeter cubed. So basically the initial burette reading, the initial volume. So initial volume or burette reading. The final volume or final burette reading. And then the last one, and you do need to write it this way, is the volume of blank added. And what is the blank added in this case? What is in the burette? So you have to make sure it's the right thing. FB2. So in this case, it's the volume of FB2 added is what we're looking for, or the volume of hydrochloric acid. This is going to change for whatever FB you're given. on any given laboratory. So next class, it may not be FB2, it might be FA1. Read carefully. What's in the burette is what's got to be here. Okay? So then the next thing, you're going to write here a heading, titration number 1. You can also write, instead of titration number 1, you could write experiment 1 if you just like generic experiments. You can say experiment 1 or trial 1. You can also say trial 1. But I always do titration 1. This is the first accurate titration. And so your initial volume, and I'm going to now give you sample data. Again, this is the sample data I'm going to work off of. Where should we start our initial volume? We want to be very 0.00. Do I have to put centimeters cubed in this box if I already put it at the top? I don't. I only have to put it either at the top, and so I should also put it here. Or if I don't put it at the top, then I have to put it in every box. One of those two ways. But you have to write the correct unit, which is centimeters cubed. Final volume, I'm just going to give you some sample data, 24.35. What would your volume of FB2 be added here? What would this be? 24.35 minus 0 is 24 point. I'm going to give you another sample data, titration number 2. So then this is just sample data we're going to use to work off of. 0.00, 24.25, 24.25. So for Mark 3, you have to have your headings. What do we mean by headings? So where is Mark 3? Having the specific initial volume, centimeter cubed, final volume, centimeter cubed. So basically taking the initial volume you read, the final volume you read, and then subtracting the 2 for each experiment. That's Mark 3, just so you're aware. Mark 4. Mark 4 is every reading is rounded to the nearest point, 0, 5. So readings are all to the point 0, 5. Meaning that if you had said this is 24.3, you don't get that mark. It has to be to the nearest 0.05 on your burette. So that's Mark 4. Is to say that every reading is to the nearest 0.05. If you see 24.3, write 24.30 or 24.35. Always to the second decimal place. That's Mark 4. You can control that mark. You can give that mark. And Mark 5. Your 2 closest accurate titrations must be within 0.1 of each other. So 2 closest titrations within 0.1 centimeter cubed of each other. So would I get the mark for this sample data? Yes. If I have this mark and I still go and do a third titration, guess what? I lose that mark. So you have to know to stop. You stop when you get 2 that are within 0.1 of each other. That you got the color change. Where you needed it within 0.1. Yes. That needs to be 9, 0. Or else you don't get the 4th mark here. All right, so these are 8 marks out of a 16-mark lab. It's for recording data correctly, writing your titration table, and then your accuracy. That's 8 out of 16 marks. How much of the lab is that? That's half. Half of the lab is recording your data correctly, the way they want you to, and for getting your accuracy marks. Accuracy marks, the only way you can control that is to have good lab procedure. Because the best way I can tell you, which we practiced last time, and you're going to practice again next class, but you'll be able to do it slower. So far, so good? Good to move on? So where are the other 8 marks?
The calculation.
Calculations. A lot of calculations in this. It's a quantitative lab. So we're going to take a look at the other 8 marks. Lucky for you, the first calculation mark is always the same. It's always the same. You can predict it. And it's quite possibly the easiest calculation to do. Don't mess up on it. Let's take a look at what it is. From your accurate titration results, calculate a suitable mean value to use in your calculations. Show clearly how you obtain the value. Anybody know what the mean is?
Average.
Anybody know how to calculate an average of 2 numbers? So, good news and bad news. Good news is that's correct. Okay? If you show clearly 24.35 plus 24.25, divide that by 2, and you come up with 24.30, you have 1 mark. 1 guaranteed mark right there. So how could we mess this up? Notice how it says show clearly? If you do it in your calculator and you don't actually show what you did, or there's another way to show it, but if you don't actually show it clearly, even if you have this correct answer, which is an easy answer to get, they won't give you the mark. So make sure you show it clearly. They're very picky here. What is the other alternative way if you don't want to show the work and you just want to do it in your calculator? If you just want to do it in your calculator, you can do the following. Put a star next to the 2 titrations you want to average. They accept this as saying, these are the 2 I choose to take the average of. What can't you do? Average 3 or average 4 different titrations. It has to be the nearest 2 that are within 0.1 from each other. Got it? You can put a tick there or a little star to say that you are using those 2 values for your calculation. They accept one of those 2 things. All right, so that was mark 9, right? This was technically mark 9 out of the 16 in the lab, is the average. The average will always be there. Look for it. Do it. It is the easiest 1 point you could possibly get. Every point's built the same on a Cambridge exam pretty much. Get that point. Don't mess up on that one. Next one, calculations. You mess up on your math, but you can give your answer to 3 or 4 sig figs, and that's how they accept it in this mark scheme. I looked at it. If every one of your answers, even if they're wrong, they're all to 3 or 4 significant figures, guess what you get? You get a point for that. So the 10th point is to give all of your calculations to the correct amount of significant figures. So far, so good? All right, so we got 6 more marks. Now we're gonna get into the real math. So wait, we got a 10 out of 16 possibly without even barely touching any of the math. Well, I was just gonna ask you. This is a 16-point lab that the kids actually took last year. Like this was the one that my students took. How many marks are actually on the lab paper altogether? This is 16 for one lab, but how many marks are in total in the lab? 40. Anybody know what the average passing on a chemistry paper 3 is? I don't mean pass rate, but it was like 80 last year. But my question is, how many marks? Because that's what we care about. How many marks are needed for a passing score on a lab exam on average? Out of 40. 15. Around 15 out of 40 is a passing score. So the lab is totally passable. You could easily get 8 to 10 marks without touching the math on the titration. And that's some students' strategies. They're like, gonna do the lab, gonna write my tables, moving on. Forget the math, blah, blah, blah. Please do that, Mark, don't forget that one. And then they go do a different lab. and they get all the marks they can there on the easy stuff, and they hack it that way. But if you want an A level or a B level on the lab, and last year multiple students did get A levels in the lab here at CIE, then you got to do the math. So I got to teach it to you. So here we go. The last 6 marks. First question says, calculate the amount in moles of hydrochloric acid present in the volume of FB2 in part B. What does that mean? Okay, they're looking for moles. So I'm going to underline that because it's what I'm looking for. FB2 in B. What is B telling me? The average amount that was needed to change the color. So at the neutralization point. So we know from part B, the information we have is we have 24.30 centimeters cubed of FB2. We know that we needed that for the titration. Or is there something missing? We gotta have something else. Now you're gonna go back to the information from the beginning of the lab. Was there a thing of, did they give me any more information about FB2? Something that could potentially be very helpful. They gave us, right in the beginning, they gave us concentration. You see it? That's the other piece of information we need. So from the beginning, we have that there is 0.0460 mole DM minus 3 of FB2. So we have the volume and we have the concentration. What's the formula? What's the formula? Concentration equal mole over dm cubed. That's the formula. You need that formula for titration. So now plug in the numbers you have and solve for what you're looking for. So you've got 0.0460 equal moles over what number on the bottom? Do we leave it at centimeter cubed?
No.
So it's 0.0243.
Now you can see why I taught it that way. So it's quick. 0.0243. Now multiply both sides by that. Multiply 0.02430 times 0.0460. And how many significant figures does Cambridge accept? 3 or 4. So double check my math. I did it earlier today. I got 0.001118. I just did it again and got the same thing. Did you all get that? Yes. Go ahead. Or 1.12 times 10 to the negative 3 if you want to go that way. Your choice, right? Scientific notation or not. Okay, so that was point number 11. So we're up to 11 out of 16. And remember, the math isn't always going to be exactly the same. You have to look at what you have and what you're looking for to figure out exactly what you're going to do. So let's see what comes next. This is point 12. I'm just marking them as we go along. Oh. What's that? Give the equation. Did you forget what that was? Might have. I think the last homework had some ionic equations in it. The one that I told you if you need help on it, come tomorrow. What's the ionic equation? It's going to be the reaction, but it's not going to include the spectators. What's the reaction? Maybe go back. This is where I suggest. What's the reaction? What are we reacting?
HCl and
HCl plus X2CO3. Why don't we sketch that on the side here? What is that? What type of reaction is that?
combustion.
That would require oxygen. Double of XCl and H2CO3, but does that ring any warning lights?
H2O plus CO2.
Every time you're supposed to make H2CO3, you actually make water and carbon dioxide. Do I need to balance this? I would say a 2 here and a 2 here. So now let's translate that to the ionic equation. I have here the correct actual full equation, but what's the ionic equation? They give us a clue. They tell us, oh, look, CO3 2 minus is part that you need. What's the spectators here? Can you figure it out? The X part and the CL, right? So just that. That's all gone. So then what's left? We got the CO3 2 minus. What are we putting that with?
H.
H plus. Was there a certain amount of H plus?
2.
Okay, so let's write that. 2H plus. On the other side, what wasn't the spectator?
H2O and CO2.
So those are the two blanks that they have. The H2O and the CO2. Do I even have a single mark?
No.
I do not. What am I missing?
State symbols.
So what would CO3 2 minus be in the flask? What's the state of that?
Liquid.
Not liquid.
Solid.
Liquid would be if it's just pure.
Oh,
It's in water. It's aqueous. All acids are also aqueous. Water is what state? And CO2 is
Gas.
little bubbles. That's balanced. That's balanced.
Question I'm not getting.
That was mark 12.
Yes, we did the first question.
If you want to write a 1, you can, but you don't have to. Up to you. Ones are always implied. You want to go back to how I showed the reaction? So the products made are here. This is aqueous, aqueous, and aqueous. So the chlorine and the X are spectator ions. That's why they're not included. I'll pause to give you some time. Why do you think they made you balance an equation? What do you think of summing this? To a geometry. Meaning going from moles of one thing to moles of another. All right. That was mark 12, right? Out of 16. We still got 4 more marks to go. You get 2 hours. And like I said, some students just breeze through and do all 3 labs first. They get all the easy recording marks and table marks and like go for the easy math. And then they do the thing that takes brain power last. Some people just do one experiment at a time. They do their favorite. For some people, titration is their favorite because it is very predictable on exactly what you got to do. For some people, qualitative is their favorite, which is the one where you like mix things and try to figure out what the unknown is. That's going to be our very last one we look at. But you have whatever strategy you want to use. What we do at the end of the year, just to let you know, after I go through all the different styles of labs with you in April and May, I do what's called a lab walkthrough, which means you get a 2-hour class period where you get to do all 3 types of labs, potentially, in a past practice paper. And you get a feeling for what that 2 hours actually gets to feel like, and then you do it again, and then you get better at it. The first time is always a disaster, and that's okay. I had somebody last year who on their first walkthrough, they had a U, they ended up with a final grade of A, like in the actual Cambridge exam. So it's just, you gotta get a feel for that timing. It takes, you get to finesse it, but you gotta practice in order to get better. Let's go to mark 13. 13. Calculate the concentration of X2CO3 minus XoCO3 and mole DM-3 in Fe5. So what do we have right now? Like, what did we have? And the labs always kind of lead you on. What did we get in the last math question? We got the moles of HCl in what? We got the moles of HCl present in Fe2. Well, what's the reaction? The reaction is we took Fe2 and we mixed it with Fe5. And the color changes when you are at the proper stoichiometric amounts. So that means when 2 moles of HCl equals 1 mole of X2CO3, that's where the color changes. So using that information, knowing that I have the moles of HCl it took for the color to change, can I figure out the moles of X2CO3 from there? So I've got 0.0001, make sure I don't add any additional zeros accidentally. 0.00, I totally did. 0.001118, like that. 2 zeros, right? And then that's my moles of HCl. So can I figure out, first of all, how many moles of X2CO3 this is equal to? The ratio right here. It's 2 of the acid is for 1 of the carbonates. Are you okay with that? We're using the stoichiometric ratio, moles to moles. So this is where some students get lost. It's 2 moles of H plus, which is the same as HCl because it's strong acid, because the spectator ion's not being shown in this ionic equation, is for 1 mole of CO3 2 minus. It might have been easier to see if you were looking at the full equation, which is here. 2 moles of HCl for 1 mole of X2CO3. This is the same equation. Ionic equations sometimes are confusing to look at because you're missing parts, because you're missing the spectator ions. But it's the same equation I wrote here. It's that mole ratio. So basically divide by 2, and when I divide by 2, I get 5.589 times 10 to the negative 4 moles of CO3 2 minus. Where do I have the mark? I went from moles of Fe2 to moles of Fe5, right? That's what I did. I have moles of Fe5. Do I have the mark? I need the concentration. Well, how do we get concentration? Concentration is moles divided by dm cubed. So it's actually 5.589 times 10 to the negative 4 moles divided by what? What's the dm cubed of Fe5? Is there a way I could figure that out? Where can I pick up the information for the volume of Fe5 in the reaction?
From the question.
Go back to
25 centimeters.
it's in the procedure. And that's what's both easy or confusing about the lab. The math you need is somewhere written in the procedure. You added 25 centimeters cubed of Fe5. It says so in your titration, doesn't it? So if my dm cubed is actually 25 centimeters cubed, what's my dm cubed then?
0.025.
And that's what we would put at the bottom here. Divide those two numbers, and we get 0.02236. And I've got mark 13. Mark 13. How many more marks we said in this one? We got 3 more marks. every mark in the lab. You don't. The top was set last year that anybody's ever gotten. Somebody got a near perfect score in the lab last year. I've never seen it. Because before that, the highest setting that I had was like a 31, 32. Somebody got a 35 out of 40 in the lab last year. Never seen it. That means they went through and they pretty much buzzed through all these marks. So it's not, it's close to impossible to get a perfect score, but it's not impossible. It's just time is an issue, for sure. Yep, which comes with practice. All right, so we've got 3 more marks here. The next mark is where I would say most students drop off, meaning even if you know like your normal strategies, this is where you're like, say what? The next question asks, what is the molar mass of X2CO3? Where could we get information for that? But we don't know what X is. So but that means we've got to come up with it experimentally. It's got to be done experimentally. So once again, what information do we have that could help us out with that? We know we've got, looking back, we know we've got the concentration from the last question, right? Go ahead. We've got 0.02236 moles per decimeter cubed, right? We've got that from the last question for FB5. This is FB5, just to make sure we're on the same page. Is there anything else we have about FD5 that could help us to get molar mass? What's the formula for molar mass before, or the formula for moles even? That has to do with grams. It's moles equal grams over molar mass. So if I want an experimental method to get the molar mass, you would multiply both sides by MR and divide by moles. So molar mass is grams over moles. So this is the technique we're going to have to take in order to solve. Okay, so I've got the concentration. Is there anything else that's in this formula that I have? Anywhere in the lab? Look through the lab. Look at the beginning of the lab. Is there something that could help? There definitely is. It's about finding it, right? Finding the number. What do you think? Let me know if you give me a suggestion. Yes.
1.3 grams of FD5.
Yeah. Which I had labeled over here, didn't I? When we were going through, I said here, when we initially made the first solution, right? We took 1.30 grams, and the first thing we did, which seems like forever ago, right? The first thing we did was we took 1.30 grams of FP3, we dissolved it in 250 centimeters cubed of water, and we named that FB5. So let's write that down, see if that. So from experiments, we know 1.30 grams is dissolved in 250 centimeters cubed. So what do we do to get the molar mass? We have the amount of grams in 250 centimeters cubed. We have the amount of moles in how much volume? In how much volume is this concentration? Rewrite it out again. 0.02236 moles is in 1 decimeter cubed. Right? 1.3 grams is in 250 centimeter cubed. You've got to match the amount of volumes. They've got to be the same, or else your work's not going to make sense. You have an amount of grams in one volume and an amount of moles in a different volume. How could you match the volumes so that they cancel? So which one would you change? Okay, so you're going to change centimeters cubed to? So this would be
0.25 decimeters cubed.
okay, so it's in 0.25 decimeters cubed. So now what?
Multiplied by 4.
That is the right time. So the idea is to look at the difference in the volume. I actually look at it, it's easier for me to compare the centimeters cubed for some reason. I know that this is 1,000 centimeters cubed, this is 250 centimeters cubed, so this is 4 times the volume that this is. You just have to compare the units correctly. So you would need to multiply your grams to match them by 4. So you do 1.3, and this is what they say in the mark scheme to do. 1.30 grams into 50 centimeters cubed, multiply that times 4 so that it matches. So you get 5.20 grams in 1 decimeter cubed. Does that kind of make sense? The trick is that there's 2 different units going on as well, so it gets confusing. Now that I have the volumes match, 5.20 grams in 1 decimeter cubed, 0.02236 moles in 1 decimeter cubed. Can I now use this formula?
Yes.
Totally. So you would do 5.20 grams per decimeter cubed over 0.2236 grams per decimeter cubed. Because this is the same on top and bottom, it cancels. This is moles. Moles per decimeters cubed. And you get the grams over the moles. So do 5.2 divided by 0.02236. And I got 232.6. Check to see if you did the same. I call this a hard mark. I don't know if you do. I call that a difficult mark. I think that's where it goes ARI. If it doesn't go ARI at the ionic equation, it goes ARI here. Yes. Somebody's up. Come back. I believe so. Yeah, Janie's up. Once you have this, can you figure out what the relative atomic mass is?
Yes.
What would you do?
Find the AR of CO3.
Perfect. So you know that this is 12. You know that this is 16 times 3.
Which is 48.
So altogether that adds up to 60. So we know that the CO3 part is 60 out of how much?
232.
So you would do 232.6 minus 60, which is 172.
Yeah, 176.
That sounds right. 172.6. Divide that by. That equals x2, right? What's x?
Divided by 2.
Divide by 2, and you get 86.2. Or is it 86.3? 86.3. 86.3. So then, welcome back. Next for the bathroom. Okay, so that was mark 14. This was mark 15. Mark 16 is to do what?
Identify that one.
How are we going to do that? So X2CO3. Is there a way to differentiate? Because 86.3, if you look, rubidium and strontium are right there. Is there a way to know which one it is? Is there something else? The charges. This is a -2 and this is a +1. You must pick the group 1 metal that's closest,
So
which is rubidium. That's it. That's mark 16. Look at how easy, after you got that, it was to go get those other marks. Now, question. You had no clue what to do here, and you put in a random number. Could you then get error carried forward for marks 15 and 16?
Yeah.
You know what to do? Yes. If you know the steps to go through and like how to analyze it, you totally could. Now, is your answer probably way off? Sure. Yeah. But could you still get those marks? Yeah. Those, but not that one. That's what we call error carried forward. You should make use of it as you get to questions that you could possibly do. All right, so the lab math is no joke, is it? But if you look at it, how many marks were pretty easy to get?
4, 5.
The first 8 or even 9 or 10, because 9 is just an average, 10 is just significant figures. After mark 10 here, it gets a little bit increasingly difficult as you go along. So I would suggest looking over this before you do your lab next class. I wanted to make sure to fully go over how to solve the lab type math. Concentration formula, absolutely necessary to have on hand. The molar mass formula, absolutely necessary to have on hand. The other one is the dilution of solutions. Sometimes you need M1V1 equals M2V2, depending on the lab. So I've got your homework. You can start working on it. There's about 13 minutes left in class, so you can start working on it. It's on Redox. Paper 1, paper 2 questions. And remember, next class is a full lab and it is a grade. So we'll be going in the grade book. So make sure to study for the next one. Write your tables correctly.
Those, come on, man. How did you not catch that? Those right.
There you go.
How do you
Start working on the homework.
I have 2 staples together.
Oopsie.
Yeah.
Because
Just take off the bottom.
parabola. Those, the form.
And grade. The lab on Wednesday, you will have partners. You'll be working with a partner again. And you will have about an hour and 15 to an hour and 30 minutes to do the lab and the calculation by the end of class. Yes. Okay. The two, yeah.
Remember that the second one was slightly larger than the first one?
I'm being very honest, that was actually like 3 days of class. But I only had one paper. Not paper last year, no, just the online. I will open it for you in there. You're welcome. All right, let me hit stop recording now.